I'm explaining the Catapult project. So here is a diagram of Catapult project. You have a Catapult here, and here is the arm of Catapult. So you pull this arm back, and then this rubber band is stretched. So the difference in the length of rubber band is denoted as elastic distance, and it is shoot and it stop here, and this distance is called range of projectile, or dx, and the time of the marble in the flight is called air time. I already measured the mass of the marble is 0.004 kilograms. 0.004 kilograms. Okay, I will explain how to calculate launch velocity. So launch velocity is denoted as VI, and x component of launch velocity is VIX, and vertical component of launch velocity is VIY. So the velocity when the marble is launched is launch velocity. So to find out horizontal component of launch velocity is distance of travel divided by air time, and y component of launch velocity. So when you look at this picture, when it goes up to the peak, the y component of velocity is 0. So at that moment, it doesn't go up or down. It stops there in a moment. So Bfy equals 0, and we need to find out the y component of launch velocity. So final velocity equals initial velocity plus at, because y component is influenced by acceleration. So at the peak, Bfy is 0. So to find out Biy, you subtract at from each side. Then Biy equals negative at. This a is acceleration of gravity, which is negative 9.8. I usually teach gravity acceleration is 10, but here in experiment we have to use accurate number. So acceleration of gravity is negative 9.8. By the way, the time it takes for the marble to get the peak of the trajectory is actually half air time, because air time is start from here and goes and stop here. So actually the time it takes to the peak is half air time. So you have to use half air time. Then y component of launch velocity is 4.9 times air time. Okay, so now launch velocity is actually the resultant vector of horizontal component and vertical component. So you have to use Pythagorean theorem to find out launch velocity, which is Vix squared plus Biy squared, and then you take a square root. Then you can find launch velocity. Maximum projectile height. Maximum projectile height is this one. So we know the time it takes the marble to reach the peak is half air time. So using this equation, which is distance equals initial velocity times time plus 1/2 acceleration times square, we can find maximum projectile height. When you use this equation, you have to use y component or vertical component. So initial vertical velocity times t is half air time. So air time divided by 2 plus 1/2 negative 9.8 times air time square. Launch acceleration. So a marble starts from rest, and its speed at each launch is launching velocity. So acceleration is launching velocity minus the initial velocity, which is 0, divided by time launch. So this time launch must be measured by you while you are doing experiment. Launch momentum. So the formula of momentum equals product of mass and velocity. So mass of marble is 0.004 times launching velocity, which you got from the first calculation. Launching force. To find the launching force, you can use the formula F equals ma, or momentum impulse theorem, which is J equals delta P. Since we know the launching acceleration and mass, we can use force equals ma. So mass of marble times launching acceleration. Initial energy of launch. So first step is to find work done to stretch band. So work equals force times distance. This force is launching force you exert to stretch the rubber band backward. And distance, this distance is the distance the band is stretched. So you measure this distance while you are doing this activity. So multiply these two variables or quantities, then you get work done on the band. Energy stored in the rubber bands. Work energy theorem states that work is equal to change in energy of the system. So work done on the rubber band is stored as elastic energy in the rubber band. So work is equal to energy stored in the rubber band. Elastic constant of rubber band. So now, since you know elastic potential energy of the rubber band, you can use this formula. Elastic potential energy equals 1/2 kx squared, where k is rubber band constant and x is the distance the band stretched. So you need to rearrange this equation for k. To get k alone on one side, you multiply each side by 2, then 2pe equals kx squared. And you divide each side by x squared. Then you have k equals 2 elastic potential energy over x squared. So this elastic potential energy is what you got just a minute ago, and this distance is you measured during the experiment. So don't forget to square. So after you finish calculation, so I'd like you to write a discussion about this project. So first, what did you experience through this project? Second, what did you find through this project?